What is quantum computing? A quantum computer is a computer that exploits quantum mechanical phenomena. On small scales, physical matter exhibits properties of both particles and waves, and quantum computing takes advantage of this behavior using specialized hardware. Classical physics cannot explain the operation of these quantum devices, and a scalable quantum computer could perform some calculations exponentially faster than any modern classical computer. Theoretically, a large-scale quantum computer could break some widely used encryption schemes and aid physicists in performing physical simulation. However, the current state of the art is largely experimental and impractical with several obstacles to useful applications. The basic unit of information in quantum computing, the qubit or quantum bit, serves the same function as the bit in classical computing. However, unlike a classical bit, which can be in one of two states, a binary, a qubit can exist in a superposition of its two basis states, a state that is in an abstract sense between the two basis states. When measuring a qubit, the result is a probabilistic output of a classical bit. If a quantum computer manipulates the qubit in a particular way, wave interference effects can amplify the desired measurement results. The design of quantum algorithms involves creating procedures that allow a quantum computer to perform calculations efficiently and quickly. Quantum computers are not yet practical for real-world applications. Physically engineering high-quality qubits has proven to be challenging. If a physical qubit is not sufficiently isolated from its environment, it suffers from quantum decoherence, introducing noise into calculations. National governments have invested heavily in experimental research aimed at developing scalable qubits with longer coherence times and lower error rates. Example implementations include superconductors which isolate an electrical current by eliminating electrical resistance, and ion traps which confine a single atomic particle using electromagnetic fields. In principle, a classical computer can solve the same computational problems as a quantum computer given enough time. Quantum advantage comes in the form of time complexity rather than computability, and quantum complexity theory shows that some quantum algorithms are exponentially more efficient than the best-known classical algorithms. A large-scale quantum computer could in theory solve computational problems that are not solvable within a reasonable time frame for a classical computer. This concept of additional ability has been called quantum supremacy. While such claims have drawn significant attention to the discipline, near-term practical use cases remain limited. Quantum computing is a revolutionary model of computation based on quantum mechanics, the science that explains how matter and energy behave on the smallest scales, like atoms and subatomic particles. Let's break down every core concept and part in detail. Number 1. Classical versus quantum computers. Classical computer uses bits 0 or 1, processes one computation at a time, follows classical physics, limited in solving very complex problems. Quantum computer uses qubits 0, 1 or both simultaneously, can process many possibilities at once. Based on quantum mechanics, can potentially solve certain complex problems exponentially faster. Number 2. Qubits, quantum bits. What is a qubit? A qubit is the basic unit of quantum information like a bit in classical computing. It can exist in superposition, being both 0 and 1 at the same time until measured. It's typically implemented using systems like trapped ions, superconducting circuits, photons, spin states of electrons. Number 4. Entanglement. What is entanglement? A quantum phenomenon where two or more qubits become linked, such that the state of one instantly determines the state of the others even if far apart. It creates correlations that can't be explained classically. Why it matters? Entanglement enables powerful multi-qubit interactions and is key for quantum speedup and error correction. Photon spin states of electrons. Number 5. Quantum interference. What is interference? Quantum states can interfere constructively, amplify probability, or destructively cancel out. Quantum algorithms manipulate qubits to boost the right answer and cancel wrong ones using interference. 6. Quantum gates and circuits. Just like classical computers use logic gates and or not, quantum computers use quantum gates to manipulate qubits. Examples. Hadamard gate H creates superposition. Poly X gate X like a NOT gate. CNOT gate entangles two qubits. TES as a gates apply phase changes. These gates are reversible and represented by unitary matrices. Quantum circuits. A quantum algorithm is built from a sequence of quantum gates applied to qubits, forming a quantum circuit. Number 7. Measurement. At the end of a quantum computation, qubits are measured, collapsing their quantum state to a classical outcome 0 or 1. The result is probabilistic, and repeating the process many times gives the final output. Number 8. Quantum speedup. Certain problems that are hard for classical computers become solvable efficiently with quantum algorithms. Number 9. Real quantum hardware. Types of quantum computers. Superconducting qubits, IBM, Google. Trapped ions, photonic qubits, Xanadu. Topological qubits, Microsoft Experimental. These require extreme environments, near absolute zero temperature, isolation from noise and vibrations. Number 10. Quantum error correction. Why it's needed? Qubits are fragile and error prone from heat, noise, etc. Quantum error correction, QEC, uses extra qubits to detect and fix errors without destroying quantum information. Examples: surface code, Shor code.